All right, day five of Advent of Code. If you give a seed a fertilizer, it's like if you give a mouse a cookie, the mouse never leaves. I think there was a moose in that book. You take the boat and find the gardener, managing a garden, water source. Island is the water source. We ran out of sand to filter it with. This is just it's a link to Wikipedia sand filters. It's a snow factory. They've turned it off for more than a few weeks. We agreed to their request, like every day. While you wait for the ferry, maybe you can help us with our food production problem. The latest Island Almanac, also a Wikipedia link, just arrived and we're having trouble making sense of it. Our puzzle input is the almanac, lists a bunch of seeds that need to be planted, also what type of soil to use with what type of seed, what type of fertilizer to use with what type of soil, what type of water to use with each kind of fertilizer, and so on. Each type of seed, soil, fertilizer, and so on is identified with a number, but the numbers are reused by each category, so soil 123 and fertilizer 123 aren't related to each other, or aren't like definitely related to each other. So seed to soil map, soil to fertilizer map, fertilizer to water map, water light map. Oh, there's a lot of things here. So seed number 53 corresponds to soil number 55. Is it destination and then source? Yeah, okay, the first one is destination. That's why I was getting confused. Of course, it's destination and then source. And of course, this is written as source destination, which is reverse order from the way the actual input is set up. Okay, so let's at least pull this in so we can look at it inside of our code base. I can already tell you this one's going to be one of those ones though. In my head, what I want to do is I want to make a type for each of the destination IDs so that I don't mess this up. Man, I really wish soil to fertilizer, but fertilizer is the first. So today we're going to write, I think, a non-parser here because I don't want to deal with splitting all of this up with white space and stuff. But maybe we also use nom supreme today. I don't think I have nom supreme in the dependencies here. I do have it in the workspace. So I'm going to do non supreme workspace equals true. I do it the long way here because I like the idea that I could come in here and add features and stuff. So let's work day 5, part 1. Failed to load manifest. Did I mess something up? Nom supreme is a dash. Cool. So we can pull in tag. There's a tag in nom supreme. I don't remember if we have to use the error type for that. We'll do this because the return type isn't relevant yet. Let's pull in tag from, no, that was a macro I think that we were pulling in there. Okay. Then we pull in the parser trait for nom. We handle our error and now we can get started. Okay. So tag seeds, and we should be able to do this fairly easily. Nom supreme, sorry, not nom complete. Nom supreme offers us a additional trait so that we can do things like this, which makes nom parsers a little bit more succinct to write. I know a lot of people have been saying that they don't prefer the longer form, but I'm going to kind of mix them right now so you get a sense of what it can look like. I'm not going to do this super succinctly because I think I'm still concerned about what the actual problem is. But here we can do tag seeds, and that precedes a separated list of U32 separated by white space. And we can start with parsing that. And then we get this vec of string slices here because I put these in the wrong order. I think it should be like that. And now we get a vec of U32s. Perfect. So those are our IDs. There is a really small trick that I would love to do right now. And that's kind of give each of these IDs. So seeds, right? We can do seed ID with a U32. And then if we map over this parser, we can do this. And then what we get here is a vec of seed IDs instead, which means that we can have Rust ensure for us that when we're doing all of these kind of range things and whatnot, that we are accessing the right one. I think that I will show that in a refactor though, because everybody else that watches the video is probably going to do it without that. So let's start talking through that way, and then we'll come back and we'll do this new type based approach. So we should have our seeds here. I'm going to instrument this with the right module path. Instrument is a tracing macro, which allows us to put debugging information in here. And I think that the debugging information is going to come in handy today. I did happen to set it up yesterday inside of day 4 for a different reason. So I'm going to take this test log crate and I'm going to bring it in. We already have the tracing crate and the tracing subscriber crate, which are really important. But this will allow us to set up logging in our tests. So basically what I'm doing is this is going to be a supercharged version of like println. So I'm going to be able to do something like this and write seeds here. And we'll bring this in from tracing info. And one thing that you may see when doing this is that the trait tracing value is not implemented for some things. So in this case, I'm going to use the debug formatter, which is special tracing syntax to put this question mark on the front. This is not a generic Rust thing. This is a tracing library specific thing. And then in our test here, instead of using test, I'm going to use, what is it? Test log test. And it's basically the same thing, except for the fact that it will let us actually set up that subscriber collector for the tracing. So if I do rust log equals info now, and we work on day one, then inside of our test process, provided I've set everything up correctly, we should be able to start seeing logs. We aren't actually calling our parser in our process function, so I'm going to start by doing that. And then we can do below that. I did let input stuff, which is our regular nom format. I'm going to use parse SeedMaps as the name of this function up here for our parser. And then we expect that to work all the time because advent of code only gives us valid input. And now we see our expect is failing on the space before 79 because let's look at the actual input for a second, because I want to make sure my assumptions about what we're doing here pan out, given that there is a lot of stuff going on here. So I think we always have one space here, unlike yesterday when we had variable space. So I'm going to leave this as seeds space. And then I'm going to do something a little bit odd. And I'm going to do this layout for a moment. So this is the tracing output right here. In this case, this is all of the input and stuff. So I don't necessarily want that context, but it gives you an idea of what this is capable of. So right here at the end, it says seeds equals 79, 14, 15, or 55 and 13. That's exactly what we want. It's coming from day 5, part 1 module, and it comes from the parse SeedMaps function, which is called from the process function. So what we have here is our initial here log, which is in our test right here. So this is the first log that comes out, this info right here. It comes out in this format with a timestamp, a log level, basically all of the spans down to where we log this event, and then the event. So if there was information to log for each of these spans, for day 5, for part 1, for tests, etc., that would get logged here. That is what's happening right here. So in process, if we look at that function, we've instrumented this function and we passed input as a string slice to this function. So this instrumentation is putting that information in our sort of like the context of our logs for us. So in our parser, when we log seeds with a debug formatter, we're getting seeds and we're getting that array, but we also get all of the context for how we got there. In our case, though, this isn't super useful. So I'm going to skip input entirely, I think, for process. So you can see that process no longer has input here. And then similarly for parse SeedMaps, I think what I'm actually going to do, we'll skip input and then we'll do fields. And we'll define a new field called input first line, maybe. And we'll set that equal to input dot, what do we do here? Split new line dot next dot unwrap. I think that's all good. We need one more parenthesis here. But now what we should get for that parse is a much shorter list of our seeds. So now what we get is the process function, the parse SeedMaps function, the input first line value that we set up for this span, the seeds that we have here, and then all the way into the actual value that we're logging out, which is the seeds. So we need to continue our parser here. Now we've got seed to soil map. So let's do, it's a little awkward. I think that because this is set up in this way, we are going to know the ordering. I think the ordering is consistent, right? It's always top to bottom. Seed to soil, soil to fertilizer, fertilizer to water, water to light, light to temperature, temperature to humidity, and humidity to location. Okay, so we can set up these as hash maps, and I don't think we need the names. So this is going to be all of the maps, I think. We have a variable number of lines here. So I think we can take until map, and map is end of line. Yeah, so we don't have white space here. And this is just going to precedes map because we also need to take that off. I'm just going to keep doing this until we get a separated list 1. And this is going to be each of the lines. So it's going to be a line ending, and this can be many 1. Line ending precedes line. I got a little bit of formatting going on there. So I will bring take until in. I will bring line ending in. Line is something that we are going to write. And then many 1. This could be fold many 1 later. But we're basically looking for a line ending line, and line is going to be destination, source, range, right? So I think with this line function that we are going to have to write now, we're going to take the input, we'll stick tracing on it so that we get our spans and whatever. And then I think we're going to pull in range. So we need to import that. It comes from standard ops range. And then this is always destination, source, number, right? Yeah, okay. So this is always going to be, we'll let input, and then this will be destination, source, I'll call it num equals tuple, and then input on the end with the error handling. We'll to do this for a second, get the type stuff to work out. Tuple we need to bring in from nom sequence. This is going to be a parser that parses 3 different or n different parsers into a tuple struct. Ranges need to be specified as well. So whatever we're going to use here, like U32. So we do complete U32 precedes a white space, and we do this twice, and the third one doesn't. We could have done a separated list. We could have done a couple of things here. I am getting a type error. What is our type error? Expected a function closure found string, right? Because these need to be tags if we're going to write it this way. So this would work. We could also just do these like in an order straight through. I'm going to leave it like that for now. And this isn't precedes. This is going to be preceded by. So those types should change from string slices to U32s because we want the U32 to come through, which is wonderful. So now we have destination ... destination plus num. We're going to stick this in a tuple and do this again. And then source ... source plus num. And I'm going to stick OK around this. We're going to get rid of that to do. We're going to stick the input here, and that's all good. So now we've got the OK to our result, returning the tuple with the input and our value, where our value is a tuple, and we've got destination and source. And what I'm going to do, because I know this is going to help me, I'm going to do source and then I'm going to do destination, because I am not going to remember to do like 1 and then 0 for the indexes. So this is it. This is what we do each time. This gives us each line. Each line is going to be 2 ranges. I do feel like this should be a struct now that I'm thinking about it. I'm going to call this SeedMap. We're going to go source with a range of U32s and a destination with a range of U32s. And the reason I want to do this, let's derive debug here because that's always useful. And the reason I want to do this is because I want to do something like this. SeedMap with a function called translate, I guess. I don't know what to call this. And this pops out a U32 for us, and we'll to do implement translation from a number to a destination. If I can spell destination. There we go. And instead of this, we'll call this source. So this will be source. It will be a U32. This function will be responsible for taking the source range and translating it to the destination range. This feels like there's an optimization to make here, but I want to get through this first, and then we can always go back and change it. So now we have these lines. We've got this line ending. I guess these are going to be really a vec. So this will be mappings instead, and it'll be a vec of maybe tuples of these. It's a little unfortunate that we lose the source and destination there, but that's fine. So vec, range. So anything in this turns into that for each of the tuples that we have. Mappings is what we really need here. Mappings is going to be this many one. So we've got our lines here, and we've got a seed map. I'll call this mappings, I guess, because that's what it is. Check our Rust messages. Call expression requires function. That is absolutely true. So again, we've run into this 1 or 2 times before. If we define parsers in a way that is unique, or we use nom supreme or something, or we're just doing something weird and we want to build something up and call it later, we can't do that without calling a function. So like in the future, we might be able to do this for that, but right now we have to do .parse. So we've got maps, and maps should be, here's one seed map, right? Take until map, precedes map. Maybe we take this and we put it somewhere. So I'm going to type this out quickly. This is going to return a seed map. We're going to get this, and I think we can just clean this whole thing up. Cool. So this is take until map, take the map off, parse the mapping. So we can just do that many again. So I think this will be many one seed map input, and this is all of our maps, right? Vec of seed maps there. And what we return from this is going to be, okay, input maps. We don't just want the vec of seed maps. We also want the seeds, which is a vec of U32s. So we'll do this as a tuple. So vec of U32s, comma, seed map. So we've got seeds and maps. And yeah, now we can do the actual logic. So I think we take this input, right? Well, we're not going to actually use this input, but we're going to take this seeds, mappings, or I guess we'll call this maps. So that gives us the list of seeds and the list of seed maps. And we need to seeds.iter.map, quite literally in this sense, seed. And this is going to be a whole thing. I think I'm going to do maps.fold, so .iter.fold. And my thinking here is that we need to maintain some state. That state is going to coalesce into a single number, and we just need to iterate through everything and keep that number around. So this starts with seed, and then we get the seed and the map. Now we can do map. Did we implement this on seed map? I thought we did. Translate, yeah. But we have a reference to a seed map here. And the issue here is going to be something related to references, I feel like. SeedMap translate. This doesn't take a self. So the error we have here is no method translate found for reference SeedMap. There's a shared reference to SeedMap in the current scope. This is accurate because it's an associated function, not a method. Usually the distinction between these two doesn't matter at all. So people will call things methods, people will call things functions or associated functions. But in this case, what that means is that we aren't taking a reference to self. And then our seed is also a reference, so we pass that in as a star. And instead of next seed here, we'll do seed equals the return value. We'll dereference that because it's mutable, and then we'll return seed. There does seem to be an issue with that. Seed is an AND reference, so the data it refers to cannot be written. Oh, are we not iter muting? Okay, so something that is relevant here is that we defined seed right here. We captured seed and then we passed it in here, but we didn't make a new copy of it. So we're just referring to the old one. And we don't really want to do that. I really kind of want to keep that around. So I'm going to use a dereference here. And because primitive types like U32 implement the copy trait, COPY, this will get cloned, or more accurately copied. And then what we get here is just a U32. So then we don't need that, and we can just do this. So what we end up having here is this seed comes in as a U32 then. This map.translate is the logic we need to translate from some number, which is generic over all of these. Like they all do the same thing over and over, right? And then at the end, we just end up with this number, which should be the location. This will be locations though, right? Because we're iterating over the seed, we're mapping the seeds, we're iterating over the maps to find the location for each seed. So this will come back into a vec. Should be a U32s if I remember correctly. Maybe not though. Let's see. Because I'm using this semicolon right here. So item iterator or iterator item change to unit here is what that's saying. And that's because I had this semicolon right here. So the return value of this expression gets eaten by that semicolon. So if I remove that semicolon, then we have this whole iterator chain here. We get the locations, and then we want locations.iter.min, if I remember correctly. And this is going to give us a little bit of an issue because min returns an option. So we will expect should have a minimum location value. Okay, so that is all of our stuff. We need to implement this translate function, but we've brought this down all the way into implementing one translate function, and then we should be done. What was the answer for this so that we have our test set up correctly? 35. So this is going to be 35. So we have our test, we have our parser, we have our logic. It looks like I messed up the parser a little bit. Where's 50? 50, 98. We had that line ending there, right? Oh, right. Space 1. This is multi-space 1 because we want to include new lines. That's the seeds, though. That's the wrong spot to do that. So many one seed map input. Seed map is where we need this. We need this. Line ending precedes line. We're already at 50. So this needs to be not preceded by a space. Why did I think the first one was preceded by a space? This is the second and the third one that are preceded by space. So now we need to implement that translation. Our parser is working, or at least getting through all of the input. And I really like, yes, the way that I'm writing the non-parsers is a little bit verbose here, but the absolute ability to just kind of work with them and maintain them and change, like, do we need this to be a space or a multi-space or a line ending or what, like all of that is really nice. So now we need to implement the translation from a source to a destination. And this is the confusing logic, I suppose. So given a source, we need to iterate over self.mappings to find the valid location. We'll call this valid mapping, right? And then we'll match on valid mapping, which is going to be an option because that's what find is, or that's what find returns, sorry. We need to iter over mappings, which is fine. And then I'll to do in here to get that type out. One thing that the Rust compiler will tell you is if a function expects to take arguments. So in find always takes one argument because you're trying to find that argument. So it's telling us that our closure takes 0 arguments and we expected one that takes 1. So we'll call this mapping. And then a valid mapping here, we can fill match arms with Rust Analyzer. And this is going to be source and destination. I feel like for the destination, we only need the start value, but we'll see. So for none, where we're going to return the source number again. So maybe we do let else here. Let else is really interesting syntax. So let some source destination equals valid mapping. And then else right at the end here, semicolon on this. And this has to return a type called never. So we have to return from this function, which is exactly what we actually want to do. We want to return source there. So now we've basically destructured this tuple, this source and destination, out of the valid mapping if it exists. And if it doesn't exist, we kind of early return here. Love it. So now we've got 2 ranges. And at this point, after we've done our find, we know that the value is in the source range. So I think we need to find the offset in the source range. Let's write our find first, because find seems easier. This is a mapping, which is 2 ranges, right? So we only care about source range here, and we only care if source range contains source. This will have to be a reference so that we can pass it in and check. Again, contains isn't doing anything to source, so it takes a reference to whatever we're passing in. And I believe this will trigger the valid mapping for everything. So then we get source and destination, if that finds one. If it doesn't, then, it doesn't, whatever. And my big question right now is there a way for a range in Rust to give me the index at which a value exists inside of this range? And there are definitely ways to build that functionality, but I'm really curious to know if it just exists. And actually, now that I think about it, what if we did something like source.start ... Oh, I named these both the same thing. That's not good. Let's fix that. Let's move our thing over here so we see this whole function. And let's call this source range and destination range, because we need to be clear about that, because I named this source already. So source range.start will give us the start value. We can go ... to source, and I'm not sure if this is ... or ... equals. So I'm not sure if we need to include the last point, but if we do this, then this should be our offset, right? I guess we could also do source minus source.start. So this would also give us our offset, and then we don't have to deal with the ranges. That makes more sense. So we've got our offset. It's a U32. And then we need to do destination range dot start plus offset, right? And that should give us the value. Wait, that didn't just pass our test, did it? I think that just passed our test. Let's kill that and run it again just to make sure. Yeah, our tests are passing. So that's valid. Whatever we just did works. So with that in mind, I'm going to cargo run day 5, part 1, and we are going to get an overflow. So that's possibly because we need to use U sizes and not U32s. 55, line 55, 26. So destination plus num. Can I throw a debug on this? And we'll see which one fails. Destination plus num equals this. Actually, I can't do that because I need to do that before it gets in there. So destination and num. So this plus that. And that does look like it barely breaches the max value for a U32, which we can find by doing this. So 4294967, 4294967,296. Yeah, literally one over a U32. Okay, I don't know if that's in there intentionally or not. I wonder if any of these numbers are that big. Yes, some of them are, and some of them are already very close. So like this one right here is 429, and then you have to add 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so we need to use U sizes here for sure. So we don't have actually a U size in num, we have a U64, but on most platforms, U size is going to be a U64. So what we're going to do here is take everything in the entire document. I hit Command D to select all of the U32s, and I'm just going to change this to U64. And then I'm going to get rid of our tracing here. I'm going to run that. That seems fine. We need to get rid of the debug that I put in there, because that's making quite a bit of noise. Day 5, part 1, passing. Day 5, part 1 gives us a number. And I really hope this is the right one, because these kind of puzzles can get very hectic if it's not. Gold star. Woo! All right, so as usual, we'll do the deep dive later. We're going to continue to part 2, get this done. Everyone will starve. Oh, if you only plant such a small number of seeds. Rereading the almanac, it looks like the seeds line actually describes ranges of seed numbers. The values on the initial seeds line come in pairs. Within each pair, the first value is the start of the range and the second value is the length of the range. That's easy for us to make a change for. The first range starts with seed number 79 and contains 14 values. Second range starts with 55 and contains 13 values. And now, rather than considering 4, we need to consider 27. I assume this blows up our processing time, and that's why it's like that. So in the example, lowest number that can be obtained from the seed number is 46. So let's start by taking all of this, dumping it into part 2, making our test 46. And what we're going to have to do here is change our seeds. So we've got seeds here, right? Somewhere. Parse SeedMap seeds, space 1, U64s. So right here, we've got a separated list, space 1, U64. we have two options here, or we have multiple options here. But since this is a separated list, let's look at our input quickly. Input all the way at the top is a whole bunch of seeds. So we need to make sure that we have all of them. So we cannot hard code that. So this will be a separated list space 1, but it's going to be a complete U64. And this is going to be a separated pair 1. I think it's just separated pair. So separated pair U64 tag space, because the space is always consistent. We need to bring this into scope, and then the typings are going to be wrong. So we're going to map over this. We're going to get start and end. We're going to do start end. Well, not start and end. This is start plus offset. We'll call this offset. So that should map us into a range. We do still have an issue. We do get a vec of U64 ranges, which is great. That is not what our return type is. So we'll do this. There's an issue with separated pair. Function takes 3 arguments, 2 were supplied. So we're going to do another complete U64 here. So now we've got our separated pair, which is U64 space U64. That is in a separated list in the same exact location we had it before. We have this doing a fold in our process right now. And then we need this up here to be individual seeds. So flat map, range, and flat map is going to basically flatten this for us. I guess, could we just call flatten here? I don't know that flatten knows what to do with a range. Yeah, ops range, U64 is not an iterator, so we can't just use flatten here. I am going to use flat map here to be a little bit more explicit. There might be another function we could use, but I'm going to flatten this. So we're going to take our ranges. We're going to take each range. We're going to flatten it into all of its individual seeds. It looks like we don't need a reference here anymore. Let's actually read what the compiler is saying. Type U64 cannot be dereferenced. That's fine. And then this is a move issue, cannot move out of range, which is behind a shared reference. That is because this range is a shared reference. That is totally fine with us. Ranges, when it comes down to it, the struct that is a range, and why I'm choosing to clone here, is that a range is a start value and an end value. So if we look at this range in the standard library, this range struct is defined as a start index and an end index. That's it. That's all a range is. It's 2 numbers. And then when we iter, it generates everything in between that. So cloning this is literally cloning 2 numbers, which we're doing all over the place anyway. I'm not worried about it. Did that work? I think it looks like it did. Test day part 2 works. So let's run part 2. And I actually don't know. So my guess is that the reason that they had us do it like this is because it was going to take a very long time to run, because these are going to be ranges now from, 0 to U64, which is a very large number. So the question here is the way we implemented this fast enough to finish the problem for part 2? Or do we need to do performance work now? Let's see how many seeds we need to deal with. So I'm going to stop this from running. It was running for 1 minute and 20 seconds. I'm not too worried about that. The one thing that I want to do is see how big this range is. So these are our numbers, and that is this many values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that a billion? I think it's just before a billion, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 235 million seeds for the first one. We could do a progress bar. I don't necessarily think that we're doing anything performance intensive here. Let's take a quick look. Our translate function is going through the mappings and just using contains, and then doing pretty basic math, like addition and subtraction is what I mean by basic math. So we're not actually evaluating the range until here, or not here, but in process. We're not evaluating the range until here, at which point we go through all of the maps and we do the translation. I feel like they wanted us to work backwards, like there's a trick to know or a better way to set it up. But at the same time, this may be a great opportunity to use Rayon. We don't have Rayon in our cargo TOML, so I'm going to bring it in. So we've got Rayon here. Rayon is a library for, well, let's look at what they say. So Rayon is a library for data parallelism in Rust that makes it easy to convert sequential computations into parallel. And then something else that we could use is actually Indicatif, which would give us a progress bar. Wouldn't that be fun? So we would actually know how long this was taking. So maybe we do that first. 17.7 is the current version. I'm going to grab this. And I don't think I have it in our root yet. So here, do I have Indicatif? It doesn't look like it. Let's drop that in here. It's 0.17.7 for the current version. Indicatif. My French pronunciation is so bad. Part 2, really the thing we want to check the timing of is this, or not the timing, but the progress. So let's start with, when we use Indicatif, we need to bring in certain traits so that we can have progress on these. I think we can just do .progress. We do need to trigger it kind of to bring down the right version. Oh, I misspecified the version of it. Oh, I put a comma in here. That's what happened. So yeah, progress not found. For some reason, Rust Analyzer is really chugging on this one. There we go. We're going to bring in that trait. If we look at the top here, we've got Indicatif progress iterator. That is the trait on which that progress function exists. And if you're sort of unfamiliar with the term extension trait, that's what this is. This is an extension trait, or a trait that provides an extension trait. So let's go look at progress iterator. That's the trait that we're using for this one. It says progress with, try progress, progress count, and progress with style. These are all functions that we can now use for anything that implements iterator and is sized. So what this does is when we bring this trait into scope, it provides these functions when what we have is an iterator. So we're effectively extending iterator with additional functions. So if we run this, we should see a progress bar, unless I messed something up. I wonder if the number is too big. It does seem like it's not really progressing. We are running this on something that eventually collects, but we are running it a little bit early in the process. So that 1 of 10, I think that 1 of 10 is actually our list of seeds, seed ranges, that is. So we need to put this below it, which I think we can't actually do at the moment because we don't know how many items are going to come in. So exact size iterator is not implemented. That's totally makes sense. Is there a way we can give it the information it needs? We do have these additional functions. So progress with a progress bar, try progress. We'll see the progress function needs to have exact size iterator implemented, which we no longer have after expanding those ranges with flat map. We don't have the count, so we can't provide the count, and we can't do progress with style. So if we want to do this, we have to get the size. So if I chop this up like this, do we get what we need? Method cannot be called on vec. Yep, because this needs to iter. Well, we want to into iter because everything else will work out if we do that. So then we run this, and it almost looks like that flat map is the issue. Like expanding that range is the issue. There we go. So now we've got a progress bar. This is for everything, actually. So 1, 2, 3, 4, 5, 6, 7. So we're doing about, we'll say 1 million every couple seconds, and we've got to get through 1 billion. So that's not really going to work for us. So one of the things we can do here to kind of, push our way through this is use Rayon. Using Rayon is actually going to be fairly simple for us, is the way that I'll put it. Oh, the other thing is it's always good. I'm doing cargo run here. I'm not doing release mode. We haven't actually had to do release mode for any of the others because they've run so fast. But compiling and running in debug mode or dev profile does mean that your program is going to be way slower. So you can see this already, right? We were running at about a rate of, I want to say 1 million processes every couple seconds. But now we're running at a much faster rate. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have to get to 10. So we're at 3. We have to get to roughly 14 here. And you can see this progress bar already spinning up. Now, this is obviously brute forcing it. This is very obviously just doing all of the work. And usually these problems with advent of code, they expect you to think of a trick or think of a different way to do this. I don't think of one right now off the top of my head. So we're going to stick with brute forcing it and see if we get the right answer. It is kind of nice to have something like Indicatif when you do this, like getting this progress bar, because otherwise we would have no idea how long this was going to take. So that gives us a number. Is that number the right number? And it is. So part 2 we've got, which is wonderful, absolutely wonderful. Usually when I run into these problems in advent of code is both the issue that it takes a long time and also that the logic is hard to write. But this time I think we got through it just fine. I'm going to commit this. Okay, so that's in. And now I want to use Rayon. So what I'm going to do is I'm going to do into par iter, and then I'm going to bring in the 2 traits that we need. And it looks like we need Rayon iter parallel iterator here. And we're just going to run this again. So all we did was locations.into_par iter. We brought in a new trait for progress, and we brought in a new trait for map. That is parallel progress iterator for Indicatif. That is into parallel iterator and parallel iterator for Rayon. So now we run this, and we're doing 1, 2, 3, 4, 5, 6, 7, 8. Okay, honestly, insert blue screen there because that Rayon stopped the AV1 encoder I was using for OBS to record all of this, and it took too long to respond to OBS, so OBS just stopped the recording. So I hope I just saved everything before this point, but I definitely just ran my computer so hard by parallelizing everything that OBS decided it didn't want to wait. So that all finished. That took 1:50 seconds, 1:49 seconds. I will put the number on the screen for how long the other one took. I believe it took longer. I don't remember. I'm going to check in the recording. So we're probably not going to run benchmarks today. I'm going to be honest. For a thing that runs for 2 minutes, I think that we have pretty obvious work to do. We don't really need to run the benchmark. Running DAT is also tough on something that runs for 2 minutes. Obviously, this is the brute force approach. If you figured out what the trick was, what we should have done algorithmically, let me know in the comments. I would love to come back with an improved version of this, but this is something that I think anybody can do. Anybody can come up with this approach, and Rayon and Indicatif were really useful for this. Starting with our deep dive into part 1, we had to write this parser, right? So we've got seeds, we've got maps. We have to take each of these seeds, run them into these maps, get numbers out, run it into this one, get number out, run it into this one, get number out. So we wrote a parser again. The parser, not too bad today. It's basically we take until the map, we build the maps. We used nom supreme today. Nom supreme includes a parser extension trait. It also includes an additional tag, which we didn't really make use of, but it includes additional error messaging. In this case, we took the input and we used tracing today too, so that was fun. We'll use tracing more moving forward. In this case, the nom supreme parser extension trait gives us the ability to do dot precedes here or dot preceded by, which makes it a little bit more straightforward to write chains of parsers. So we tag seeds colon space, and that precedes the separated list, and we parse that out, and then we get a vec of U64s here. And then we parse the seed map. The seed map is a similar thing. We just ignore everything until we get to map. Take until doesn't parse the map characters as well, so we need to parse the characters out for map. And that is all before we build up our seed map. Our seed map uses ranges. So we've got our source and our destination, which I ordered to be the right order for my head. So source is the first one, destination is the second. And then we've got the list of seeds and the maps. We iterate over the seeds. We map each seed into its full chain of maps by using fold. So we iterate over each of these maps. We use the translate function that we defined, and we collect those into a U64. We actually, now that I think about it, don't need to collect here. We could just run min here and get a single number back. I'll probably make that change later. And then the translate function for our seed map takes some source, some seed, throws it through any mapping that it might find. If it doesn't find a mapping, we use let else syntax to either destructure these variables into the scope or return the source number, because that's how it works. It's an identity if it doesn't match. And that's it. That's not too bad overall. I think that the interesting part of today is the variety of libraries we used to sort of debug and make sure that we were headed in the right direction. And then once we were headed in the right direction, actually knowing how long our program was going to take and whether we needed to parallelize it ahead of time, and then parallelizing it. For part 2, the change to our parser was fairly small, so we left basically everything alone, and we turned the U64s into ranges instead. Once we had those ranges, we chose to use the same exact logic, right? So we took the seeds, we flat mapped over these ranges. This flat map and this clone of this range turns this into a very large set of numbers, which is fine. We did that so that we could get the progress bar. We don't necessarily need to do that. So now that we know how long this takes, or approximately how long this takes, we could probably refactor this code to not show the progress bar and thus not build up this range ahead of time and collect into it. But we did that, and we used basically the same logic that we had before, and we minned again. The interesting part for part 2 was we had a really long running program. We didn't do the algorithmically optimal thing. We instead chose to let that program run. And then after that program ran, we chose to speed it up using Rayon, using into_par_iter, which is just a parallel iterator that we pass into progress, which gives us the progress. And then we get to use the same exact logic we did. And because this is parallelizable, everything just worked out pretty nicely for us. So let's take a look at the leaderboard. It looks like the same couple people are at the top. Siegfried is back in the top 3, along with Looking for Internship and DeFellow. I feel like today we're going to see a little bit of drop off in the early times. We've got 34 people, it looks like, maybe 36 if we count a couple down here, that are done by the time I'm done with the video. So congratulations to everybody that got something done today. I feel like the rules days are, you know, a little bit difficult, not necessarily because of the problem themselves, but because there are so many rules to read through and so many words that map to concepts but are intentionally not giving you the concept, like a range. I think we had 2 or 3 paragraphs dedicated to saying that that was a range. And then there's also the problem of it taking a really long time. So if you do something slightly more inefficiently than usual, you kind of end up down a hole waiting for your program to run. So if you have any questions, leave them in the comments as usual. If you are working on Advent of Code yourself, join the Discord in the description, and I'll catch you in the next video. Have a great rest of your day.